So it's good to get into the habit of thinking about, because not all diagrams will be, that you won't be given a scale, so you might have to come up with a scale for yourself to fit the appropriate size. So this might be 1,000, this might be 1,000 nautical miles, in which case you probably use 100 to 1. Or it might be 500 feet, in which case you might use 100 foot to 1 or something like that. So it's up to you to choose the scale to fit the appropriate example. So, of course, let's do the calculation again just to show you that it works. So we'd be doing obviously the same calculation, so exactly the same calculation we did over here. So it'd be 50 squared plus, which of course is going to be 130 nautical miles. So on your diagram you can now check that by putting the ruler on there and measuring it and check, oh yes, it should be 10 to 1, so this should be 13. So on my diagram it should be 13 centimetres, but it's representing 130 nautical miles. So I guess you've got to get used to that idea that all the graphs we're going to draw during this course, they're not necessarily what they are. They're representing something. So the graph represents something that's much bigger or on a different scale, or it could be, these could be other things. I mean, for example, later on we'll draw graphs which have fuel flows in them and graphs which have speeds in them and velocities and that sort of stuff. So a graph can represent anything, not just distance. All right, so let's say we wanted to calculate those angles now. So here's our formula. So if I was using my diagram, it would be 5 over 13, but if I was using this diagram, it would be 50 over 130. But notice that's the same. 50 over 130 is the same as 5 over 13. So the numbers that we're going to get from the diagram, of course, are going to be the same numbers in terms of the angles. This angle here is going to be the same angle we've got over here. So your diagram, so you can check your answer. I don't know if you've got protractors here with you. You can check that by measuring the diagram, measuring that angle there. And then, so it's a good habit to get into to do the calculation and then check your answer from your diagram. So here's our formula. Okay, so we want to turn that formula around. We know it's going to be, we can see from the diagram it's what about 25 degrees or something. Is everyone agreeing? It's about 25 or maybe a bit less than that, 20 degrees, something like that.
How would you use this big one? You have to draw a figure.
Just extend that line out to make it longer.
Oh, okay.
So it overlaps the edge of the compass. So put the centre of the square on the point of the triangle. So put the centre of the protractor here. Can I borrow you?
Oh, yeah.
Can I borrow it so I can actually show on camera? Yeah, like this. So if you put the centre of your protractor there on the point and measure that up angle there.
Oh, yeah, right.
So that'll be 10. So on my diagram, I'm not saying my diagram is accurate, but on my diagram it looks like about 22 degrees.
Yeah.
Does everyone see that? That's just going anti-clockwise from that point. Obviously you can sorry. Got away with me. There we go. Yeah, try that. So it should be about 20, is that about right? About 20, 20 something degrees? Okay, so we have to now know how to do that. So that's how we can do it practically with our diagram, but we also need to know how to do it off the calculator as well. So we've got to, let's think about this. So when we get to this stage, we've got an inverse function, which the inverse of squared is square root. So when we got to here, a squared equals 169, we then get, okay, I've got to get rid of the squared, so we use the square root function. So the same thing applies here. The sine has an inverse function, and it's called literally inverse sine. Inverse sine is written sine minus 1, but it just means inverse of the sine function. So we're inverting the sine function to get back to the angle now. So we're calculating the angle whose sine is 50 over 130. So when you calculate it, you're just going to press, you'll be pressing shift sine. So just try that in the calculator. Shift sine or inverse sine. And then bracket. So shift sine. Notice you can either put 50 over 130 or you can put 5 over 13. Of course it's going to give you, man, my diagram is so accurate. It was 22 degrees. So you normally only use 1 decimal. So well, let's say just practice our rounding. If we rounded it to 2 decimals, it would be 22.6. 2 degrees. Is everyone getting that to work? So So you don't have to, as I say, shouldn't be trusting your calculator completely. You should be also looking at the diagram and saying, okay, does that seem right? Is it 22 degrees? If your diagram is saying 28 degrees or 31 degrees, that's not good enough. It's got to be pretty much spot on. So get into that habit of trusting your diagram. It should work. So what will the other angle be? So let's call this angle alpha up here or something. What will the other angle be? Well, the 180 rule. So remember that 180 rule, the angles of the triangle set up to 180. So if we subtract the other angle, that should give us the other angle in the triangle. Remembering that total has to be 180, so if you subtract the other two from 180, so at 180 minus the other two angles, that should give me the third angle. Or you could just go 90 minus 22.62, that of course would give you the same result. Okay, that's since we're practicing our, we know everything about that triangle now. We know all the distances, we know, so let's turn this into an aviation example. So the aviation example might be something to this effect. Okay, the destination point is, I'm taking off from airport here, flying from say airport A to airport B. I've gone, the location here is 120 miles east and 50 miles north. What's the track? What's the track of that line? Now you've got to remember track is relative to north, so there's north there, so on my map, you might want to mark that on your map just to remind yourself. The north is there, so actually when you say track you mean the angle clockwise from north. I'll just put that there just to remind you. So when you say the word track, you mean that angle here. That's the track. And again, that's completely arbitrary in the terms of we've chosen north as 0. I mean, that's a human choice. We could have chosen south as 0 as well, but we didn't. Or we could have chosen any direction as 0. But we chose north as 0, and we choose clockwise as positive direction. So when you say the track, you're really saying, well, what's that angle there? And of course, that angle there, anyone see what that angle would be? That track angle?
No, it's the track.
Yeah, because see, that's right. That's a 90 degrees. That's 90 degrees there. So those two angles have to add up to 90. So the track would be just 90 minus that angle which we already worked out, which is 22 point, let's just use one decimal, which will give us that third angle, which will be 67.4 degrees. 0.067, I think you guys are right. Oh, I can't understand it unless you write 0.67. So you're familiar with those sort of terms, are you? Yeah, okay. Yeah. So 0.67, so your track would be, from this point, to get from that to point to that, the track would be 0.67, tracking 130 miles a mile. By the way, notice these opposite angles are equal, so it's a nice little rule to remember. Opposite angles, like a Z rule, so if you think of that sort of Z shape, so if you've got a line like that and then two parallel lines, opposite angles are always equal. They call that the Z rule, for obvious reasons, because that makes sort of a Z shape, so if you think of that there, the Z shape. So these two angles and also the opposite is usually worried at small angles. So that angle there, look at that Z shape there, that angle there is the same as that one. 67, which we already worked out up here. So 67.4, 67.4.